Can anyone just tell whatever you remember from week 1?
Linear combination,
Okay. Then
span,
yes, good.
basis, spanning set,
Very
change of basis,
yes. So when you talk about basis, what is the other word you study together with basis? The number of elements in basis is called dimension, right? Dimension, and then the very important topic, vector space.
subspace.
Yes, good. So these are some topics which we have covered from week 1, right? So now in week 2, we will study about, see, in week 1 you are introduced to vector spaces, particularly R2, right? Now we are going to see functions, particularly this linear transformations. These are the specific type of functions in R2. So linear transformations in R2, this is what we are going to see mainly in week 2, and the various aspects of linear transformation. Okay, in today's session we will try to cover maybe up to range and null. Okay, and the remaining we will cover in the upcoming sessions. Okay, we'll try to cover as much as possible till probably till range and null space. Okay, fine. So matrices is the first thing we are going to see in this week. Why matrices? We said this unit is about linear transformation. Then why are we studying matrices first? Matrices are very important for linear transformations. So only via matrices we will be able to do some computations quickly. If you are anyway with transformations you will be able to do, but it's going to take time. If you are just using the transformations, matrices are going to simplify things about a linear transformation. That's why we are starting with water matrices, which you already are familiar with, right? You people already know what are matrices, right? So particularly, what is a 2 by 2 matrix? 2 by 2 matrix is, you have a rectangular array, or sometimes you can call grid of numbers. Particularly here you have two columns and two rows. So what are the columns and what are the rows here? So these are the columns, right? You have two columns and you have two rows, right? So these are the columns and these are the rows. Okay, so for a 2 by 2 matrix, now how this matrix comes into play for a linear equation, that we have already seen, right? So how do we get the matrix from a system of linear equations? Do you remember? So when you have two linear equations, for example like this, a11x plus a12y equal to c1, a21x plus a22y equal to c2, how are we going to write this in terms of matrices? You have A11, A12, A21, A22. This is your matrix, right? And then this is your unknown vector, and this is the constant you are having, right? So when you do matrix multiplication, you will get back this linear equation, right? And this linear equation here, you can also see the same in the linear combination form also. What is linear combination? Do you remember? So if you are having two vectors, say u and v, what is mean by linear combination of these two vectors? Let us say you are having two vectors u and v. What is mean by a linear combination of these two vectors? Can anyone tell? It is,
Alpha times u plus beta times u.
yeah, for scalars alpha and beta, alpha u plus beta v is a linear combination of the vectors u and v. Good. So same way here you see, now the vectors are a11, a21 and a21, a22. So the columns here form the vector. Okay, and these vectors are from R2. Okay, and here we are, the scalars are x and y, which are the unknowns. So this is the linear combination form, and the matrix vector form is just what I have written here. Okay, so now why are we having all these different forms? To understand that everything is interrelated, nothing is new. So linear combination is something we already know. System of linear equation, you have done solving system of linear equation in M1 itself, right? In math 1 you have done. And this is the matrix vector form. So here is the matrix form, and this is matrix vector form. So everything is representing the same thing. Okay, now let us see what are transformations, and then slowly we will see how the transformation, linear transformations and matrices are related. Okay, so what are transformations? First of all, what are functions? Do you remember in M1 you have already seen what are functions, right? So functions are, can anyone say what are functions? There are mainly two things about a function. A function should have a domain and codomain. That is the basic thing. So for a function, you have a domain and a codomain, right? So in our case, both the domain and codomain are R2 only. Okay. And here we are going to call the function usually as T. Okay. So for a function means function should take every element of the domain to an element of the codomain. So every element in the domain should have an image. Okay, fine. And that image should be unique. One element cannot be mapped to more than two elements. So these are some basic things about function. Now here from R2 to R2, the same thing. So what are these transformations? You take one vector from R2 and map it to another vector in R2. So every vector in R2 is mapped to some vector in R2. So the vectors in R2 from the domain are taken as the input, and then you are getting a vector V again in R2 as an output. Okay, so this may be looking very abstract, but when you see examples you can clearly understand what are transformations. So let us see that, for example, here let us define the transformation in this way. So T of x comma y, you are taking an element from R2. Okay, now how are we defining translation? What is translation? First of all, translation means simply moving from one point to another, right? We are just shifting the position, right? That is translation. So now we are moving every point from R2 to plus a comma b. So every point you are just going to add a comma b, so it is going to be going to shift it to x plus a comma y plus b, right? So here it is given in this graph. So suppose this is your vector, then it will be shifted to this point. If this is your point, then it is going to be shifted here. So with abstract a and b, maybe it is difficult for you to understand, so let us assume a comma b is equal to 1 comma 2. Okay, now let us try to visualize. Now can you tell me what is t of 1 comma 0? According to this definition, if we are translating to this point, your t of x comma y will become x plus 1 comma y plus 2. Now can you tell me what is t of 1 comma 0?
2 comma 2.
2 comma 2, right? So this point here, 1 comma 0, is getting shifted to this point 2 comma 2, right? So this point is getting mapped to this. So if this is your u, then this is your tu, right? And same way, for example, what about t of 0 comma 1?
1 comma 3.
1 comma 3, right? So you take this point. So if this is your, maybe this is u1, and let's call this u2. Now this point is mapped to 1 comma 3. So this is your tu2. Okay, so you see what is happening for a translation. And the origin, where does the origin go to? The origin will go to 1 comma
1
2,
comma 2.
right? So this is what is the translation. And here you see that every element of u2 is having a output here, right? So this is a translation, and this is an example of a transformation. And the next example is scaling. Scaling is something which you already know. What happens when you scale a vector, you already know. Let's see how far you remember. Let us say you have a vector u in R2. Okay, and you are going to scale that vector. Can you tell me what happens when alpha is, let us say, greater than 0 but less than 1? What will happen? What about the direction? What about the magnitude? You have to tell both. Can anyone tell what
In
happens to the direction?
direction remains the same and magnitude decreases. Yeah.
Yes, direction remains same and magnitude decreases. Good. What happens when alpha is greater than 1?
Direction same and magnitude increases.
Correct. Right? And what happens when alpha is less than 0? Maybe we just talk about the general scenario. The direction is
Opposite, just opposite.
reversed. Magnitude will depend on the value of alpha, right? So the direction is reversed and magnitude depends on alphas, just like whether it is between 0 and 1 or it is greater than 1, modulus is greater than 1, it depends on all that. Okay, so just I'm checking whether you people remember about what happens to scalar times of a vector. Okay, fine. So now this scaling operation is a transformation. So take any vector in R2 and fix an alpha, scale that vector to alpha times of u. Then you will get a transformation. So this is a transformation. So every vector u is transformed to alpha u. So for example, let us say you are having t of u is equal to minus 2 times of u. Okay. So now for this transformation, now for example, if I am going to consider the point maybe 1 comma 1, where it will get translated scale to for minus 2 comma u. So this is your 1 comma 1 vector. So what about tu? What is the value of tu?
Minus 2 2, yeah.
So you will have somewhere here, right? So it is going to be this vector. So it is still lying on the same line, but you see that the direction is reversed and the magnitude has increased. So this is t of 1 comma 1. Okay, so this is what is scaling and this is a transformation. And the next one is rotation. So in rotation, what is going to happen? Whatever vector you are having, let us say you are having a vector like this. Okay, so let us say the vector, the r is the radius, that is r is the magnitude of this vector. Okay, r is the magnitude of this vector. Okay, now if I'm going to rotate this vector to an angle theta, then will the vector be still inside the same r2? Yes or no? If you are just rotating it, it is still in r2, right? So you are going to get some other point in r2, right? So now you see, let us say the original angle it is making is theta naught. So the now the new vector is making an angle theta plus theta naught. Do you understand what's happening? This is the vector you are having. This is your u. Now u is making an angle theta naught, or maybe here u is making, I'm just saying in the reverse way. So u is making an angle theta, and now you are adding a angle theta. So that means you are rotating. You are rotating this vector u. Okay. So to an angle theta naught to get tu. So this is your new tu. Okay. So this is again a transformation. Okay, so we have seen three different types of transformations. So all these transformation, are they clear to everyone? So first one is the translation. So just shifting the position by a vector, by constant vector. Next is scaling. You are just scaling the vector, so it is going to, the vectors are going to remain on the same line. And rotation means the magnitude is going to remain the same, only the direction is going to change. Okay, because you're just rotating the vector. So all the three examples clear to everyone? Yeah, because we are going to use the same example again. If you have doubts, please ask. Okay, fine then. Okay, so now looking at linear transformations. So these are all examples of just transformations. Now we are going to specifically look at what are linear transformations. Okay, So linear transformation means it should satisfy these two conditions. What are these conditions? A transformation T from R2 to R2 is said to be linear if T of U1 plus U2 is equal to T of U1 plus T of U2. So the image of the sum should be equal to sum of the images. Okay, so the first property is called additivity. Okay, and the second one, the image of the scalar multiplication is equal to the scalar times the image of the vector. So this is the scalar multiplication property, sometimes called homogeneity, but let's stick to scalar multiplication. Additivity, scalar multiplication. So if these two properties are there for a transformation, then such a transformation is called linear. Now we have examples of a transformation. Now we will see whether these transformation are satisfying these two conditions or not. Okay, fine. Now what about this translation? First of all, given here, I should have not given the answer, but anyway, it is given that it is non-linear. Can anyone justify that it is non-linear? Let us maybe stick to the specific example if you want, or if you want to say the general case also, it's fine. Maybe first we'll start with the specific example for your convenience. Can you say why this is not linear? So either you should explain it with this or with this. It means that you should say that whether this is satisfied or not, or this is satisfied or not, you need to check. Okay, so let us see. For example, what about t of 1 comma 0? Can you tell? We have already calculated the value of t of 1 comma 0. It is nothing but, what is the answer?
2 comma 2.
2 comma 2. And we also calculated what is t of 0 comma 1. What's the answer?
1 comma 3.
1 comma 3. Right? So let us say this is your u1 and this is your u2. Okay. Now, what is u1 plus u2? u1 plus u2 is?
Comma 1,
Comma 1.
comma 2.
Now, what is t of u1 plus u2? Calculate and tell me.
3 comma 5.
1,
Answer carefully.
wait,
I'm asking t of u1
2,
plus 2 comma. See, what is t of u1 plus u2? So you have to add 1, 2 to this vector, right?
2, comma 3.
Yeah. So 1, 1 plus 1, 2 should give you 2, 3. But what is t of u1 plus t of u2? I guess someone answered this
3.
earlier. 3 and 5, right? So now, are these two same or different? Is not equal to tu1 plus tu2, right? So it means additivity fails. So even if one of the property fails, you can say that it is not linear, because for a linear transformation, you need both these properties to be satisfied. So even if one fails, then you can say that the transformation is non-linear. So this is non-linear. So do you all understand up to this? Why this is non-linear? Do you all understand? So the same will work if you just replace 1 comma 2 with a comma b, the same is going to happen. You can just visualize maybe with some other a comma b, you can try it. So up to this, is it clear? Okay, fine. So the next part is scaling, and scaling is linear. Why scaling is linear? Okay, so let's see. So now t of u1 is alpha u1. T of u2 is alpha u2. Can you say what is T of u1 plus u2? It's alpha times u1 plus u2, right? Now we can just multiply this alpha inside, alpha u1 plus alpha u2. But what is alpha u1? Alpha u1 is nothing but tu1. Same way alpha u2 is nothing but tu2. Okay, so you see that tu1 plus u2 is same as tu1 plus tu2. So the first property, additivity, is done. Okay, and what is the second property we need to check? The scalar multiplication property. So it means what? Let's multiply this with some scalar a. Okay, so a is some scalar. Okay, now this is a times of alpha u, right? Now these two are just scalars, so they can shift positions. So this is now, or you can keep it as it is also a times, so it is easier to write. Fine. So now what is it you need to show? You need to show that this is same as a times of tu. Now what is tu? Can you tell? Just tu. What is tu?
Alpha times u.
Okay. So now you see that this alpha u can be simply replaced with tu. Okay. So the scalar property, scalar multiplication property is also satisfied. So this is a linear transformation. Okay. So now for rotation, how to check linearity, additivity and scalar multiplication. First of all, rotation is not going to change. This property will not get affected by rotation. That are you able to visualize clearly? So what is going to happen? Suppose let us say you are having some vector v. Okay, now you are going to scale this vector. Now this is your, not scale, sorry, here this is an example of rotation. So now you are going to rotate this vector. So this is your tv, let us say. Okay, now if I am scaling this vector and then I'm rotating, I'm scaling this vector. Okay, and now I'm rotating. It is same as just scaling this vector itself, right? True or not? Right? So you can easily visualize that this property holds. You can visualize it. So to visualize the property for rotation, additive property for rotation, maybe it is not very easy for many people. So I have given a example here. Okay, so let us take two vectors u and v. Okay, so u is this vector. So u is this vector 1, 0, and I have taken v to be the vector 0, 1. So this is your vector 0, 1. Okay, now I'm going to rotate this vector to this point. Can anyone guess what is the angle I have rotated this? Can anyone guess? See, it is perfectly the diagonal of this square. So what is the,
45.
yes, sorry, what's the angle? I did not hear you properly. Someone answered something.
45 degree.
Yes, correct. So I have just rotated for, this is just for an example. You can rotate to any angle. So for example, I have rotated this vector to 45 degrees. Okay, so this is your T of u. Same thing I have done for V. I have rotated this to an angle 45 degree. Okay, and I got T of V. Okay, so now you see that I'm adding these two vectors. So the addition of these two vectors is 1, 1, right? U plus V is 1, 1. So this is your 1, 1. And this 1, 1, I have rotated again to 45 degrees. So you see that now the vector is here. Okay. The other thing you can see that, so now this is your T of U, this is your T of V. And when I complete this parallelogram, this vector is nothing but the diagonal of this parallelogram. So what can you say about this vector now? If this is the diagonal of this parallelogram with sides T of U and T of V, then this should be T of U plus T of V. Correct? Because it is the diagonal with sides t of u and t of v. So you can see that the additivity property will also hold. So just I'm illustrating. So in general also we can prove. Maybe for proof we need to know what is the specific transformation, that we will see maybe a little later. Okay, because I need to explain more about rotation. So for now, at least you understand what is happening in this specific case. Is that clear, everyone? Yeah, fine. Okay. So we have seen that out of these three examples so far, this is non-linear, this is linear, and this is linear. So three examples we have seen where two are linear. Okay. So now one important property for a linear transformation is that if t is linear, then t of 0 is 0. Why it is 0? You can either use additivity to prove this, or you can use scalar multiplication. Anyway, you can prove this. For example, let us consider u1 is equal to u and u2 is equal to minus u. Then what is t of u1 plus u2? Yes, can you tell? Yeah,
0.
right. So you see that it is t of 0, right? Now what is t of u1? It is simply t of u. And what is t of u2? It is t of minus u, right? Now this minus is nothing but minus 1. So can we write it as minus t of u? Right? This can be written as minus t of u, right? We know according to the additivity property that t of u1 plus u2 is same as t of u1 plus t of u2, right? So this is nothing but t of u minus t of u. So this is 0. So we can see that because of additivity, you will get that t of u1 plus u2, which is nothing but t of 0 is 0. So this is your LHS. This is your RHS. So you can see that LHS is equal to RHS. So we will get T of 0 is equal to 0. So is the proof clear? Why T of 0 is 0? Yeah. Okay. So a small homework for you. Try to prove the same property using scalar multiplication. Just for your practice. So try to do the proof using scalar multiplication. The same thing. Prove T of 0 equal to 0 using scalar multiplication. Alright. That is a homework for you. Alright. So here I'm just making a recap. So to prove that our transformation is linear, we need to prove both additivity and scalar multiplication for all points in R2. Okay, to disprove that a transformation is not linear, it is enough if we can just give one point where either additivity or scalar multiplication fails. That is what we have done, if you remember. We have just took a specific case where the additivity fails. Then we can say that it is non-linear. But to prove that it is linear, we took just a random point. It means we are proving for every point in R2. Okay. So this is the general concept for checking a linear transformation. And the other concept is that if t is a transformation and t of 0 is non-zero, then t is not linear. So now can we use that to check that this is non-linear? So this property, if t is a transformation and t of 0 is non-zero, then t is not linear. Now let's try to use this to prove that translation is not linear. How? So you see that t of u is u plus ab. Now what is t of 0? Is ab. And ab need not be non-zero, right? And ab need not be non-zero. So this is non-zero. So let us assume a comma b to be non-zero, maybe. That's clear more. So here a comma b is non-zero. So in that case, you see that t of 0 is non-zero and hence t is not linear. Okay. So you can prove one concept in mathematics using several arguments, right? So that is something very important about mathematics. So here you see that maybe there are several ways, right? This is just one way I've shown. You can choose some other points, or you can choose scalar multiplication property. There are several ways to say that translation is non-linear, right? Okay, so far are you with me, right? Is the pace all right? Am I going in the correct pace, or is it too fast or slow? Fine, right? Okay, thank you. Now, okay, so everyone try to do this problem. Just first guess and then we will check specifically. Now you have four transformations here. Can you make any guess whether which ones are linear and which are non-linear? Okay, fine. So if
B
not,
and C are linear.
okay. See, I will, for now, let us try with some specific examples. And once we finish this example, I will tell you how to check with specific formula is there for checking linear transformation. Simpler formula is there. So here, the first case for A, for example, what is T of 1 comma 1? Can you tell? What is
1
the
comma 2.
1 comma 2? Now, what is T of 2 comma 2?
4 comma 4.
Right? Now, what is 2 times of T of 1 comma 1? It is 2 comma 4, right? Are they equal? Are they equal? T of 2 comma 2 and 2 times of T of 1 comma 1, are they equal? They are not equal. So it means scalar multiplication property fails, right? Tu, so T of alpha u not equal to alpha tu. So scalar multiplication property fails. So it means is T linear or non-linear? T is
Non-linear.
non-linear, right? Okay. Now for B, why I am just going for a specific point and why I am trying to prove, you will get to know just after this problem. Okay. So now I am going to take two vectors. Let us say x1, y1 and another vector x2, y2. So what is T of x1, y1? x1 plus y1, 2x1 plus y1. And same way, what is T of x2, y2? x2 plus y2, 2x2 plus y2. Now let's add the vectors together. So you get x1 plus x2 plus y1 plus y2. So this is just addition of scalars. So I'm just shifting their positions for the next step. So next you have 2x1 plus 2x2 plus y1 plus y2. Okay. Now what is T of x1 plus x2, y1 plus y2? So it is x1 plus x2 plus y1 plus y2 and 2 times of x1 plus x2. So 2x2 plus y1 plus y2, right? So do you see that? Let us call this to be u1 and the other one to be u2. So this is u1 and this is u2. So you have u1 plus u2 here. So what is that we got? T of u1 plus u2 is equal to T of u1 plus T of U2. So are you able to see how we are able to prove additivity here? So here I'm going to give the other part as a homework. So T of alpha U is equal to alpha times T of U. You must try it for yourself. Okay. So this is a very simple one. So you can try. And the same we are going to do for C also. For C, I am going to give the first part additivity as a homework. And I will do the scalar multiplication here. Okay. So that I have done one additivity and one scalar multiplication in class. Okay. So now alpha x, alpha y. Can you tell me what is the image of this for C? What's the image? Yes, it's
Alpha x by
alpha
2,
x by 2.
alpha y by 2.
Good. Right? Now we can simply take the alpha from this vector and you will have simply x by 2 and y by 2, which is nothing but t of x comma y. As simple as that. You have done the scalar multiplication part. Okay. So already we have seen some multiplication case, something similar to this. Now can you do the same? Maybe try with the same 1 comma 1 for D and tell me what's the answer. For D, can you tell me what is T of 1 comma 1? What is 1 comma 1? Yeah,
1 by 2, 1 by 2.
1 by 2, 1 by 2. All right. Now what about T of 2 comma 2 comma 2? It is 1 2, right? And it is not equal to 2 times of T of 1 comma 1. Right? So you can see that this is not linear. So here this is non-linear. These two are linear and this is non-linear. Okay. So this problem, why these two are non-linear and why these two are linear, is it clear for everyone? I have given some part of it as a homework, but still I guess that should be easy only. Is it clear for everyone? Yeah, fine. Okay, so now, so in general, how does a linear transformation T from R2 to R2 look like? If we have some typical form, then we can quickly tell just by looking at it, right? So this is something you must know. So it should be of the form ax plus by cx plus dy, where a, b, c, d are scalars. Okay, so always every linear transformation will be of this form. Okay, ax plus by and cx plus dy. Now let us look back the same question. With this formula here, can you quickly tell whether it is a linear transformation or not? The first one, here x and y are in product. Can they be in product form? No, right? So it is not linear. Do you understand how we are able to use this formula to say that the first one is not linear? The same way you can use the same to say that this is also non-linear, because product is not allowed here, only sum and this kind of a linear combination is allowed here. Can you see that? And for this example, can you tell me what is ABCD? What is ABCD for this case? Quickly tell me.
1 1 2 1.
And for this,
1 by 2, 1 by 2.
A is 1 by 2. What about B? B is 0 in this case.
0.
Yeah, same way C is 0 and D is 1 by 2. Okay. So This is a kind of a shortcut. If you understand how to use this, then you can simply see this and you check that it is linear or non-linear. Okay, fine. Okay, let T from R2 to R2 be a linear transformation, then which of the following options are true? Okay, so the first one, T of 2 comma 3 is equal to T of 1 comma 1 plus T of 1 comma 2. Is this true or not? How to check? So you have two vectors u1, u2, and here you have T of some other vector. Now what is the sum of these two vectors? You have T of u1 and T of u2. What is u1 plus u2? U1 plus u2 is nothing but,
2 and 3.
so you see that this is T of u1 plus u2, right? So T of u1 plus u2 should be equal to T of u1 plus T of u2, right? So if it is T is a linear transformation, then A is true or false?
True.
What about B? You don't have to do any calculation. Straight away you can tell.
True.
What about C? You have T times of alpha times of 0, 0. According to the scalar multiplication property, it is alpha times T of 0, 0. But what is T of 0, 0?
0.
So it means it is alpha times of 0, 0. It is 0, 0. But it is given it is 3 comma 3. So tell me it is true or false?
False.
What about the last option? So you have u1, u2 here. What is so you have minus 3 times of, so you have to be careful here. You have also a scalar. So T of u1, so let us make it plus. So let us multiply minus 3 inside. So you will get T of minus 3 comma minus 3. So now let us call this u1 and u2. So first we did the scalar multiplication. Now we are going to look at this addition. So now what is your u1 plus u2? Tell me.
Minus 2 minus 1.
Minus 2 minus 1. So is D correct or wrong? Correct.
Correct.
Okay. So this problem is also quite a simple one. I hope all of you understood. Okay, fine. What about the next one? So you have a transformation T from R2 to R2 and it is defined in this way. So which of the following options are true? So now you are given what is the transformation. You simply have to check these values here. So first condition, T of 0, 0, this part is obvious. What about the other part? What is T of 1 comma minus 1? Just substitute 1 and minus 1 in place of x and y. What will you get? X plus
0
0 comma,
0 comma minus 2.
minus 2.
but here it is given as 0, 0. So option 1 is, option A is
Incorrect.
Wrong.
because of this here, right? This is not equal. Okay, what about T of 1 comma 2? It is
3
3 comma.
1.
1.
Okay, so here it is given 3 comma minus 1. So again B is incorrect. What about T of 0 comma 1?
1 comma 1. It is correct.
Yeah. So here it is 1 comma 1 and this is correct. What about T of 1 comma 1?
2 comma 0. It is correct.
Okay, so this is also a simple one. Okay. Suppose T from R2 to R2 is a linear transformation defined as T of x comma y is x plus y comma 2y. Okay. Now you are given that T of 2 comma 3 plus alpha times T of minus 1 comma 2 is this, and you need to find what is the alpha. How to do this? So first, just similar to this one, whatever we did here, first we do the scalar multiplication and then add it. So this part is now equal to T of 2 comma 3 plus T of minus alpha comma 2 alpha, right? And now this is equal to T of 2 minus alpha comma 3 plus 2 alpha. Okay, and we are given that it is equal to 9 comma 22. But before that, let us substitute it in this formula. Can you substitute in this formula and tell me what's the answer? 2 minus alpha plus 3 plus 2 alpha. Simplify this expression and tell me the answer. What is the first part here? Simplify it and tell me.
Alpha plus 5.
So it is alpha plus 5 comma 6 plus 4 alpha. So is the other part, did I do the calculation correctly? Yeah. Okay. So now we are given that it is equal to 9 comma 22. So it means what? Alpha plus 5 is equal to 9 and 6 plus 4 alpha is equal to 22. So now from the first equation, can you tell me what is alpha?
4.
Okay, just
4.
we can verify it by substituting 4 here. 4 into 4 is 16. 16 plus 6, 22. So this answer is correct. Okay, so your alpha is 4. So far, all the problems are clear for everyone? Okay, fine. Okay. So the next topic here is linear transformation and basis. What is a basis? Do you all remember? Okay, let us quickly recall what is a basis. If you have two vectors v1, v2, okay, for basis for R2, first of all, for R2, how many elements should be there for basis? Can anyone tell? Can there be more than two elements or less than two elements or exactly equal to two elements for basis for R2? Can anyone recall? How many elements should be there in a basis for R2? No one remembers.
2.
Okay. So there should be two elements in the basis for R2. Can you tell whether they are linearly independent or not? If they are elements of basis, are they linearly independent or not?
Yes, ma'am.
So they are linearly independent. Okay. So now you have two vectors v1 and v2, okay, which are basis for R2. Then what is the definition? According to the definition, then you take any vector in R2 that can be written as a linear combination of v1 and v2, right? So it means what? Every vector in R2 can be expressed as a linear combination of the basis elements. So just two elements are sufficient to study the entire R2. You can study the entire R2 with just two elements. You can just express any element as a linear combination of these two and figure out the properties of this element. That is what is given here. So if T from R2 to R2 is a linear transformation and V1 and V2 is a basis for R2, then T of V can be figured out for any V in R2 if we just know what is T of V1 and T of V2. How is that possible? So what is given to you, is that clear? What is given to you? Given that V1, V2 is a basis for R2. Okay. And then it is also given that TV1 and TV2 are known. So how are we going to find? So now the question is, if V is any element from R2, okay, V is any element from R2, what is TV? So with this information, how will you compute T of V? You just know what is TV1 and TV2 and you are given that V1 and V2 are a basis for R2. So how will we compute T of V? Any idea? Anyone?
We know that T of V is linear combination of TV1 and TV2.
Exactly. Exactly. So you know that since V is in R2 and V1 and V2 is a basis, according to the definition of basis, we can write V as AV1 plus BV2 for some scalars A and B, right? So for some scalar A and B. So here A and B are in R2. Sorry, R. A and B are in R. Now here, what is T of V? T of V is T of AV1 plus BV2, which is, now if you have the if you use the additivity of T, we can split it as T of AV1 plus T of BV2. So now here we have used additivity. Here additivity is used, right? And then next we are going to use scalar multiplication. So if we apply the scalar multiplication property, you get A times of TV1 plus B times of TV2. That's all, right? So here TV1 and TV2 are already known to you. Since V1 and V2 are bases, you can find what is A and B for given V. So all these values in this expression are known to you. So you can find T of V for any V. So is that clear? What is the information given to you here? Is that clear? So if you have a basis and the images of the basis for a linear transformation, then you can find the image of any vector in R2. That is what is given to you. Is that clear so far? Yeah. Okay, fine. Okay, now we are going to visualize whatever we just saw here. We are just going to visualize. So for example, here we are going to first look at the canonical basis. Okay. So now, so here instead of just any V1 and V2, I am going to take the canonical basis. So this is my V1 and V2 now. So this is my V1, V2. Okay. So now you are given this information. So this information is given. What is TV1 and what is TV2 is given to you. Now consider U is equal to A comma B. So this is your A comma B. Okay. Now you see that this is the point 1 comma 0 and your A is lying here. So can you tell whether A is less than 1 or greater than 1? Tell me. Less than 1, right? So A is less than 1. If A is less than 1, what happens to A times of TE1? So will the vector get shrinked or it will extend?
Shrunk.
Yes. So you see that this is the actual vector TE1. Okay. So your actual TE1 is up to this. Okay. So this is your TE1. Okay. But you see that A times of TE1 is here. Okay. So it is on the same line, but just the magnitude is shrinked here. Okay. Now here again you see this is the point 1 comma 0. Sorry, 0 comma 1. Okay. And your value B is here. Now can you tell me whether B is greater than 1 or less than 1?
Yeah, greater than.
So if B is greater than 1, then what happens to B times of TE2? So it is going to lie along the same direction, but the magnitude has increased. Here the magnitude has decreased and here the magnitude has increased. Okay. So here this is ATE1 and this is BTE2. So up to this, is it clear? Okay. Next, what is T of U you need to find. What is U? If you remember, U is nothing but AE1 plus BE2, right? AV1 plus BV2. So here that is what is U. Now here this is your ATE1 and this is your BTE2. So when you complete the parallelogram, this is the diagonal. So this is your T of U. Okay. So this is just the visualization of whatever we have done here. Okay. Is that clear for everyone? The visualization part? Yeah. Okay. By the way, see the strength is just 39 here. I see. May I know what is the reason you people are attending the live session here? Because many are not attending. I cannot ask the reason why they are not attending. At least I want to know why you people are attending so that I can say the same thing to the other students that this is the reason many people are attending and you are missing out this reason. Can anyone tell me the reason for attending the live session?
I was only attending.
Yeah, this is very helpful. This goes in sequence, right? All the concepts are revised, I mean, taught by the professor. It goes well, it's very useful.
So if you miss this session, what you might miss? Can you tell that?
Yeah, this adds something definitely. So it supplements some
Yes.
of the,
This aids your learning process, right? Okay. So
definitely.
okay, fine.
Yeah, I have a quick question for you.
Yeah.
So I attended the week one taught by
Mm-hmm.
you.
Mm-hmm.
Okay, I think you completed half the way. I mean, on the day. So
Yes.
I didn't see the continuation of it. Did you?
I did not teach the other part. The other instructor did the second half of week one.
Okay. Yeah, we lost the continuity because you took all the many lectures, right, in the consolidated way.
Okay.
Yeah, I think we need the some phase where the continuity is there. So yeah,
Uh,
but thank you. You are doing good job.
okay, fine. Thank you. So the point I want to say is that whoever is attending the session here, please try to attend it continuously. You also have the attendance criteria here, and also I hope that the sessions are going to be useful for you. Okay, so everyone try to attend the sessions and don't miss any sessions. Try to make the best out of every live session. Okay, fine. And if it
Can I
is
ask
in,
a
Ma'am,
quick question? Can you
yeah,
request?
please.
So I noticed the week two is
Mhm.
also due tomorrow. I think both I knew week one is due tomorrow. So is it possible to move it Wednesday? Normally it will be Wednesdays, right? The deadline.
That is what I also know, but
Yeah,
I'm
please
not.
pass on this request to whoever can make a decision.
Okay,
That
okay,
will be
fine.
useful.
Yeah, fine. I'll just inform this and check with this. Yeah.
Thank you very much.
Okay.
ma'am,
Yes.
is there any schedule of the live sessions like week 3 or week 4 schedule?
Is it not given to you?
No, ma'am. I
Bro,
don't know.
can you add
Maybe.
your calendar
Okay, then I'll just
automatically?
tell Shubham to
Again,
give the schedule. He's the lead, so he will be giving the live session schedules. I will just, I maybe he missed to share it. I will tell him to share it with you. Okay, fine.
okay, ma'am. So
Okay, ma'am.
in the calendar, the timing is mentioned for every week. So it is same or it is different from.
Where it is mentioned? Sorry, I did not understand what you said
Yeah,
completely.
in the Google Calendar, when we go to course portal and there is option to add the calendar, course calendar. So when we
So yeah,
add,
so usually you have
we have
sessions on Saturday, Monday, and Tuesday, right?
Yeah, we see the schedule in the calendar. So right, it follows the calendar,
Yes,
correct?
yes.
I see. I noticed those things.
Yeah, so Monday and Tuesday you have live sessions in the morning, and Saturday you have from 8 to 10. So this is the usual session, but if you want a separate calendar, like if you want a Google Sheet, that also can be provided, maybe. All right, fine. So let's continue.
wait, I have one more question. I am attending every
Yes.
live session. Instead, I have missed the first one. But I am
Mm.
receiving mails regarding that you haven't attended any live session or so. What is the problem? Means I am attending every live session. I think I have missed one or two at least. Yeah, I think only one. But I am receiving mails regarding that you haven't attended any live session yet.
Did you join with your official mail ID?
Yeah, I have joined with my student email ID every time when I.
Then that should not be the case. But if you continuously get the same mail, maybe you can bring the issue to discourse. Maybe. Okay, we will check that.
I think this
Okay,
mail is
okay.
forwarded to the all student. I got also, so I attended all sessions.
Oh, I see. Then I'll
Maybe it's a support mistake or something.
yeah, I'll check this. Okay.
Yeah.
Fine.
Okay.
Thank you for bringing attention to me. Fine. So let's continue here. Transformation of a line we are going to see. We have seen what is a linear transformation, how we can find a linear transformation with just the basis, with the images of the basis, and we saw the visualization. Now we will see what is a transformation, linear transformation of just a line. Okay. So what is the equation of a line? Do you remember? The equation of a line is y is equal to mx plus c. Right? So now if you take any point on a line, okay, what are the coordinates of the points on this line? Y is equal to mx plus c. So let us say you are having this, okay, and this is your line. Let's say this is your line. Y is equal to mx plus c. Now I'm going to take any point on this line. What are the coordinates of this point?
X, comma mx plus c.
Yes, x comma mx plus c. Right? So now x comma mx plus c, how can you write using canonical basis? Can anyone tell how to express x comma mx plus c using canonical basis? So you have x comma mx plus c. How will you express using canonical basis? Canonical basis means 1 comma 0 and 0 comma 1. So what are the coefficients so that you will get back x comma mx plus c? Is my question clear? So let us say you have a comma b. What are the coefficients of 1 comma 0 and 0 comma 1 when you write them as a linear combination? What are the coefficients for a comma b?
X.
A, A and B.
A comma B.
Right? So now, same way, tell me what are the coefficients for 1, 0 and 0, 1?
Yeah, x, comma, yeah, x and mx plus c.
Right? That's all right. As simple as that. So here, this is E1, this is E2. Okay, so you see that the vectors on a line y is equal to mx plus c are of the form u. In terms of this expression, it is given. So you take any vector here u, okay, so that is written as, instead of x, here t is used. That's all, nothing has changed. Instead of x, t is used. T e1 plus mt plus c times of e2. Okay, so t is nothing but your x here. Okay, it is a real number, that's all. Okay, if you want you can keep x also, but yeah, usually to write the expression where you refer a real number, we are writing t, that's all. Fine. So this is the expansion in terms of the canonical basis for any point on the line. Okay, now where does this line get transformed to under a linear transformation? That is what we are going to see here. Okay, fine. So what is t of e1 first of all? So you are having t of E1 is given as A comma B. So this is given to you. This information is given to you. This information is given to you. T of E1 is A comma B and T of E2 is C comma D. Right? A comma B and C comma D, you know that you can write the vectors in terms of the canonical basis as AE1 plus BE2, and here it is CE1 plus DE2. Right? Now what is T of U? U is this. What is T of U? You know that T of U is nothing but T times of T of E1, which is this. This is T of E1, right? And MT plus C is your scalar now. So this comes out. And this is T of E2. So should I maybe write this for your clarity? So T of U is nothing but T times of T of E1 plus MT plus C times of T of E2. Now T of E1 is this and it is written here, and T of E2 is this and it is written here. Then we are just doing some calculations here, and you end up getting this term. So this is the coefficient of E1 and this is the coefficient of E2. Okay, so T of E2 now lies on this particular line here. See, these calculations are not important. What is the final takeaway? We can maybe check through an example, that is easier for you. Okay, so for example, let me take a very simple transformation and help you to understand what is going on here. So let us say you have t of x comma y. Okay, I'm going to just explain whatever is going on with an example here. So let us say t of x comma y is, maybe let us say 2y comma x. Okay, so t of x comma y is nothing but 2y comma x. Now let us take a very simple line. So y is equal to x. So this is the line I am considering. Now I want to see where this line is going to get mapped. Okay, so it means I want to see what is t of x comma x. So y is nothing but x, right? So I am substituting x here. So this becomes 2x comma x. So this is the image. Now all the points 2x comma x. So what will it form? So y is equal to x means, so you are having this and this is your y is equal to x, right? Now what is this line? 2x comma x means what is this line? What is the equation of this line? Can anyone tell? What is your y is equal to?
X is equals to m times 2x plus yeah 2x.
So this is your y coordinate. Your y is x and your x coordinate is 2x. So what does that mean?
X
Y is
X
equal to
by
x by 2, right? So this is the, so this line will get mapped to this line. Y is equal to x by 2. Now what about another line? Let us consider the line y is equal to, let us say for example, x plus 1. Now can you tell me what is t of x comma y is now x plus 1. Now what is this? Can you tell me?
Y equal to x minus 1.
So you have 2 times of x plus 1 comma x. So this is 2x plus 2 comma x, right? So now can you tell me what is your y? What is your y? Can you tell me what is your y now? Yes.
2x plus
Yeah.
3.
2x plus 3. Are you sure? See, this is the place where you will have y. So tell me what is your y equation. So here you have, if this is confusing, maybe I will use u comma y or x1 comma x2 for you, for your convenience only. It's not required. So for example, let us say this is u comma v for your convenience. U plus 1 and this is u plus 1 and u. So here you will get u and u. So now your y is u and this part x is 2u plus 2. Now can you tell me the equation of y? What is the equation of y? So this is 2y plus 2. Tell me now. This is not
X minus 2 by 2.
yes, that's all right. So you have y is equal to
X minus 2 by 2.
x minus 2 by 2. Okay. So these kind of things you must tell me quickly the answer. Okay. You should not hesitate. Fine. So you see that now you have x minus 2 by 2 or you can rewrite it as x by 2 minus 1. Okay. Now what is the difference between these two lines here? Can you tell? Your line y is equal to x plus 1 Maybe I'll use this color. X plus 1, where it will lie? So for 0, it will be 1. For 1, x is equal to 1, it will be 2. So it is some parallel line here, right? Passing through the point 1. So this is your y is equal to x plus 1. What is the primary difference between these two lines and these two lines? The hint is here.
Shift by one.
See, note that this line,
One is through origin and
yes, passes through origin. And the image also passes through origin. First of all, how do you say from the equation that it passes through origin? Can you tell me?
No intercept.
Yes. So the C part, if the C is 0, then you know that the line passes through origin. So here you see that y is equal to x means it is passing through origin, and y is equal to x by 2 also. There is no intercept here. So it means it is also passing through origin. Okay. And here you see that this is a line which does not pass through origin. Same way here you see that this is the image is also a line which does not pass through origin. So what is the takeaway here? What is the image linear transformation of a line? A line will always go to a line, but specifically if you are looking for a line which passes through origin, then it will also pass through the origin. Okay, this is the main thing you have to see here. Okay, so do you understand the what is going on here? The calculations and all are not important, just the main concept here is important. You can just check the multiplication and see what is the value here, how we got this, that you can check with this calculation, but this is the concept here. Clear, right? Okay,
yes.
fine. Okay, so now let us quickly recall the subspaces of R2, because next we are going to look at linear transformation of subspace. Okay, what are the subspaces of R2? Just the origin, just one single point, the origin. It is a subspace. Then any line through origin is a subspace. What about line which does not pass through origin? Can it be a subspace? It cannot be a subspace, right? And the entire R2 is a subspace. Okay, so you have these three subspaces. Now, what is something common for all these subspaces? Can you tell me, just for a quick recall? One point is common for all the
Origin.
subspaces. One, yes, for any subspace, origin should be there. Don't forget it. Okay. So now let's look at what is the linear transformation of a subspace. Okay, so let us take any subspace of R2. So it should be any one of these three. Okay, and T from R2 to R2 is a linear transformation. What is given to you? The set T of S is nothing but this. What is your T of S? Set of all T of U where U is in S. So this is the definition of T of S, right? And it is given that it is a subspace. So what is the criteria for subspace? How do you check that some given set is subspace? So suppose you have some set, let us call a set A. This is a set. How will you check A is subspace?
Ma'am, if it is a subspace, then it's contain 0, comma 0 and scalar. If we will scale by some constant,
Mhm.
so that will be also in within a subspace, and if we will and it contain additivity closer under addition.
So it is closed under addition and scalar multiplication, right? So in precise way, there is a shortcut. Instead of checking addition separately and scalar multiplication separately, what is usually done? You take two elements from A, take the linear combination, check if it is in A. If this satisfies for every u comma v, then A is a subspace. So this is the condition you usually do for checking that a given set is a subspace. Okay. So here, first we are going to check whether this T of S, that is the image of S, is a subspace or not. So for that, what we have to do? We have to first of all take two elements from this set. So what are two elements from this set? So two elements are Tu1 and Tu2, where U1 and U2 are elements of S, right? And then we are going to consider some linear combination of these two elements. Now, according to additivity and scalar multiplication property, you can rewrite it as T of AU1 plus BU2, right? So now you see that AU1 plus BU2, since S is a subspace, right? Since S is a subspace, this property holds for a subspace. So AU1 plus BU2 belongs to S. Is that true or not? Right?
True.
So AU1 plus BU2 belongs to S. What about T of AU1 plus BU2? So it is an element of T of S then. Right? So what we have done here, we have taken two elements of T of S and we have shown that the linear combination belongs to T of S. Okay, so it means that we have shown that this set T of S is a subspace. Okay, so far with me? Yeah, all right. Okay, so the next thing is that this set has a dimension less than or equal to the dimension of S. Now, what is mean by dimension? Can you quickly recall what is dimension? What is the dimension of a subspace or a vector space? Here it is subspace. I am taking subspace, so it is the same for a vector space as well. Anyone? Can you tell what I even told in the very beginning of this session? What is the dimension of a subspace?
Number of bases.
Number of elements in the basis. Okay, for any subspace, there are infinitely many bases. Okay, except the zero space. You will have infinitely many bases for any subspace, non-zero subspace. So the number of elements in basis is what is called the dimension of a subspace. Okay. Now it is given that the set T of S will have a dimension less than or equal to the dimension of S. It means the dimension cannot exceed the dimension of S. Okay. So how are we going to see this? Okay. Fine. So what can be the maximum dimension of S? Can anyone tell? So we have three possibilities of S. So what is the maximum dimension of S?
R2. 2.
2. Right? The maximum dimension is 2. So I'm just going to consider that scenario. So let S1 and S2 be a basis for S. Okay. Then what will happen? Then what will happen to T of S1 and T of S2? So what I'm going to say is that claim. What I'm claiming is that T of S1 comma T of S2 spans T of S. What is mean by spans T of S? What is the meaning of this statement? Can anyone tell? I'm saying T of S1 and T of S2 will span this set T of S. Can anyone tell what does this mean?
So it means we can write T of S equals to linear combination of T of S1 and T of S2.
Correct.
So
Very good. Yeah. So what you said is correct, but just one small correction I will say that T of S is a set. You cannot write a set as a linear combination of two vectors. You can write the elements of the set as linear combination of the vectors. So spans T of S means you take any vector from T of S that can be expressed as a linear combination of T of S1 and T of S2. So how is that possible? So let us take any element from T of S. So any element from T of S is of this form, where you have U in S, right? Now, since S1 comma S2 belongs or forming a basis for capital S, Now this U is an element of this capital S. So how can you relate this U and S1 and S2? Anyone? How can we relate this U to S1 and S2? How can we use this S1 and S2 to describe U?
Some scalar multiplication alpha.
Yes. You can express it as a linear combination of S1 and S2. So you see that T of U now is nothing but T of A S1 plus B S2, which is A T S1 plus B T S2. So what is that we have done? We have expressed this T of U, okay, as a linear combination of T of U is a linear combination of T of S1 and T of S2. Okay, so this means that T of U belongs to the span of T of S1 comma T of S2. Correct? So we have proved that TS1 and TS2 spans T of S. Okay. So if this spans T of S, but what is the thing we wanted to show? We wanted to show that the dimension of T of S is less than or equal to dimension of S. How is that clear from this previous statement? What is the dimension of S from this? Is 2, right? Because the basis has 2 elements. Now, this set T of S is spanned by 2 elements. So, what can be the dimension? So, here we don't know how many elements are there in the basis, but we have a spanning set. So, what can you say about the dimension from a spanning set? Again, this property you all should know. Number of elements in a spanning set is always greater than dimension of the space. Greater than or equal to dimension of the space. Okay. Number of elements in a spanning set is greater than or equal to the dimension of the space. So here you have 2 elements in this spanning set. So you have the dimension is less than or equal to 2. Sorry, I did not write it correctly. The dimension is less than or equal to 2. So dimension of this says that dimension of T of S is less than or equal to 2. So are we done? Which is nothing but the dimension of S. Are we done? Do you understand what's going on? If you want me to repeat, please tell me. I can repeat it quickly. Is it clear? Okay, fine. Okay, so what we have done, we have shown that for a subspace S, T of S is also a subspace and dimension of T of S is less than or equal to dimension of S. Okay, so you see that for R2, okay, so if your S is R2, then your T of S can be either entire R2 or it can be S or it can be origin. Okay, either it can be entire plane or line or origin. So anything is possible for T of S. But when it is a line, you have only 2 possibilities. Why? Because this is your S. If this is your S, you cannot have T of S to have a dimension bigger than this. So this is not possible. So for this S, this T of S is not possible. Do you understand the reason? Because this T of S is having dimension bigger than this. Right? So this is not possible. And for origin, only origin is possible because the other two have bigger dimension than this. So this mapping of S to T of S, is that clear? Yeah? Okay.
So is there a different case if the line is not passing through the origin? Is
If
there
the line is not passing through origin, can it be a subspace? So S represents a subspace here.
okay, already it's a subspace. Okay.
Yes. Okay. So now here are some exercise. I'll give you maybe 5 minutes. Try to do these two exercise by yourself. I'll just give 5 minutes. Everyone try to solve these problems. We'll discuss after 5 minutes. Everyone should do this. Very basic exam problems only. Try to do it yourself. So have you all completed these two questions? Shall we check the answer? Okay. So for the first one, you are given what is t of e1 and t of e2. You are asked to find 3 times t of 2 comma 1 plus t of minus 1 comma 2. So you can do this in steps. So can you tell me what is t of 2 comma 1? What is t of 2 comma 1? How will you find t of 2 comma 1? Anyone? Okay. First of all, how will you write 2 comma 1 in terms of the canonical basis? This is
2 times 1 comma 0,
yeah. So 2 times of e1 plus
1 times of e2.
what is then t of 2 comma 1? 2 times of t1 plus 1 e2. So it is nothing but t of e2. Right? Now can you tell me what is t of 2 comma 1? I thought everyone would have figured this out. We have given this expression several times. Yeah. So now can you tell me what is t of 2 comma 1? So 0 comma minus 2 plus 1 comma 1. So the answer should be 1 comma minus 1.
Minus 1.
So what about t of minus 1 comma 2?
Minus 1 times e1
So minus
plus
e1 plus 2e2. So it is actually t of this. So minus te1 plus 2 te2. So what's the answer? The answer is 2 comma 3. Is that correct? Did you all get the same answer?
yes.
Now 3 times of t of 2 comma 1 plus 2 times of t of plus t of minus 1 comma 2 is nothing but 3 of 1 comma minus 1 plus 2 comma 3. So 3 comma minus 3 plus 2 comma 3. So what's the final answer?
Option A, 5 comma 0.
Okay. Can anyone suggest a different technique for this? Instead of finding t of two elements, I want to find the answer by finding t of just one element. How can we do that? Can anyone tell me? Yeah?
Using matrix.
No? You just simplify the expression and that's all, right? So t of 3 times of 2 comma 1 means 3 times means you get 6 comma 3 plus minus 1 comma 2, which is t of 5 comma 5.
5.
So it is 5 times te1 plus 5 times te2. So which is 0 comma minus 5 plus 5 comma 5. So you get 5 comma 0. Right? So you can do it in this way as well. Okay. Both the methods are clear to everyone? Yeah? Fine.
So, excuse me, given the T1 equal to this and T2,
Mm-hmm.
can you find the transformation behind this? Is it
Yes, of
possible?
course. Yes, of course. How can we find? So for finding the transformation, you are having T of, so T of T from R2 to R2, and you want what is T of XY. So this is what you want. So
Yep.
now what do we know? We know that X comma Y is nothing but X E1 plus Y E2. Correct?
Yep.
So it is X T E1 plus Y T E2 when I apply T. Right? So
Yep.
now this is X times of 0 comma minus 1 plus y times of 1 comma, the same thing, whatever we did, instead of just numbers, now we are having xy, that's all. So here you will have y comma minus x plus y. So this is the transformation for this particular case.
Yeah, this was the approach I was trying to do. So I wanted to get the transformation and apply these values. And okay,
Yeah.
yeah, either fine. Yeah.
Yeah.
Thank you.
Okay. So this is something which everyone should know, how to obtain the transformation from the images of the basis elements. Okay, fine. So the next question is, if T is a linear transformation and S is a subspace of R2, then the set T of S is. We already saw. So if S is a subspace of R2, then T of S is it a subspace or is it whole
Yes.
space or not necessarily a subspace? It is a subspace, first of all,
Yes, ma'am.
right? And what about the dimension of T of S? The dimension of T of S, is it less than or smaller than the dimension, less than or bigger than the dimension of S?
Less than or equal to. Yeah.
Right? So option C. Okay, fine. So this is just from the property we have seen before. Okay. Now consider a linear transformation T from R2 to R2. T of E1 is 1 to, T of E2 is minus 4 comma minus 8. So if the transformation set T of R2 lies on a line passing through the origin, okay, so they are mentioning that T of R2 lies on a line passing through origin, okay, then find the slope of the line. So what is the slope of the line they are asking. So now let us first try to understand what is going on. So T of 1 0 is nothing but 1 2, and T of 0 1 is nothing but minus 4 comma minus 8. Okay, so what's happening here? 1 0 means it is mapped to 1 2, and 0 1 means it is mapped to minus 4 comma minus 8. Now what can you say about any x comma y? What is T of x comma y? Just like we did here, can you quickly compute and tell me what is T of x comma y for this? X times 1 comma 2 plus y times minus 4 comma minus 8. So it should be x minus 4y 2x minus 8y. Is that correct? Yes or no?
Yes, ma'am.
Now observe what is the relation between the first coordinate and the second coordinate.
2yx comma 2y something like 2
Yes.
times.
So you can observe that the second coordinate is 2 times of x minus 4y. Right? So it means what should be the slope? Y is equal to
2.
2 times of x. So the slope is 2. So this is your m. So slope is 2. Do you all understand how y is equal to 2x? So this is your y part and that is 2 times of your x. So the slope is 2. So is this clear? This problem?
So this
Yeah.
slope is transformed line, right? The image
Yes.
of okay. So normally in the first problem you were showing the slope is half of the original. That's what I was observing. So yeah, so original should be then y equal to x.
Yes. So here your y is 2x. So in that case, here you had 2. I guess you are talking about maybe this one.
Yeah, all this the half
Here you
of the
have
original.
2 here. Here you have 2 here. That's why half of that. Now
Okay.
here we have 2 in the second part.
Oh, okay.
You understand the difference, right?
Mm-hmm. Mm-hmm, mm-hmm.
Yeah.
Double 2 times now.
Yes,
2
yes,
times the slope.
exactly. All right. So the next important concept of today's topic is here. See, in the beginning we had some technical issues and we were delayed by some 15 minutes. So we will try to catch up here. Okay. So that's why the session is getting extended. Usually I try to conclude it on time, but since the delay, we will extend it maybe for some more time today. We'll try to finish this topic and we'll wind up. Okay, this is a very simple topic only. Okay, so matrix of a linear transformation, how to find the matrix for a given linear transformation. Let us say this is your linear transformation. Okay, and you consider the canonical basis. This is the canonical basis. Then you see what is TE1 and what is TE2. Okay, so the matrix of T with respect to the canonical basis is defined by this 2 by 2 matrix, where the first column is nothing but the coordinates of TE1 and the second column is nothing but the coordinates of TE2. For example, see, consider this transformation here where TE1 is this and TE2 is this. So what is this matrix, can you tell? So this is TE1, this is TE2. So the coordinates of TE1 should be the first column. Can you tell me first column?
1 2
And second column?
3 2.
So the which option is correct here?
D.
Okay, fine. Okay, so one thing you should note that this thing we have already seen. So for a vector u which is x comma y, you can write it as a linear combination of e1 e2. So tu also can be found using this expression. Now the same we can see in terms of the matrix as well. So how to find T of u using the matrix? So you see that now this TE1 is nothing but AB, right? So the TE1 is AB and TE2 is CD. So I am writing TE1 as AB and TE2 as CD. Then I will write this as a matrix expression. I get this matrix expression here. Okay, so to find TU, either I can go by this way, or if I have the matrix, I simply have to find the transformation by this matrix multiplication, matrix vector multiplication. Okay, so for example, here you have this transformation here. Our previous technique tells that T of x comma y is x times TE1 plus y times TE2. So it is x times of 1 comma 2 plus y times of 3 comma 2. So the answer is x plus 3y comma 2x plus 2y. This is the previous technique. Now what is the matrix vector multiplication technique? So T of x comma y can be simply found using this matrix 1 2 3 2 multiplied to the vector x comma y. So if you do matrix multiplication, what is that you will get? First row into this vector x plus 3y, right? X plus 3y and then 2x plus 2y, the same thing. So you will get the same expression either in this technique, or if you have the matrix, you can get in this way as well. Okay, provided you have the matrix with you. Okay, so you understand both the techniques, right? So if you have matrix, you can use this technique also. Okay, so now suppose you are having a transformation T from R2 to R2 where T of 1 0 is this and T of 0 1 is this. Okay, and you are given that A is the matrix representation of T. Find the value of A plus alpha by B plus beta. I guess A and B, if it is specific, it will be easier. I don't know what was the A and B given to you. What was the A and B given to you? I guess it is varying for everyone, or how is that so?
Ma'am, we can compare this. A is equals to 6.
Okay. And B is
B should be -2.
see, this can be any A and B. Just I thought maybe if I can do some problem from which you have in your page, then I thought I can do that specific one. So are you saying that from here you are doing this, or oh,
Yes,
from
ma'am.
the
Yes,
matrix?
ma'am. Yes.
Okay, okay, fine, fine. I did not notice
Yeah.
this. Okay, okay, fine, fine, fine. Okay, so what he is saying is that this A and B are simply these values from the matrix only, so there is nothing to compute here. Okay, see, what is the first column? First column are nothing but the coordinates of T of 1 0, which are A comma 3. So this is 6 comma beta. So from here, what is your A and what is your beta? A is 6 and beta is
3.
same way. What is T of 0 comma 1? It is given as
Minus
minus
1,
1 comma b, and here it is given as alpha comma minus 2. So you can see that alpha is,
minus 1.
beta is,
B is minus 2.
sorry, b is minus 2. Okay. So now quickly calculate this value and tell me. A plus alpha, b plus beta. Answer is,
5.
all right. Okay. Okay, so this is just an matrix example. Now we will see how to obtain a transformation from a matrix. So here we saw how to get a matrix from a transformation. So given the transformation, how to obtain the matrix. Now the other way around. Now you are having the matrix. How will you get a transformation from this? Very simple. You just define T of E1 to be this and T of E2 to be this. So once you know T of E1 and T of E2, you know how to define the transformation. That's all. Okay. So earlier we had T of E1 and T of E2. We wrote them as the columns of the matrix. Now we have the columns of the matrix and we are going to write T of E1 as this column and T of E2 as this column. As simple as that. Okay. So we got a transformation for this matrix. So we can move either ways, from a matrix to a transformation and from a transformation to a matrix. Okay. Clear? Okay, so now here is a quick problem. Let A is equal to 5, minus 1, 2, 3 be the matrix of T with respect to the canonical basis. Which of the following options are true? So if it is with respect to canonical basis, can you first of all tell me what is T of 1, 0?
5, comma 2.
What is T of 0, 1?
Minus 1, comma 3.
Okay. Now T of 1, comma 0 plus 0, comma 1, what is the value?
4, comma 5.
So option A is correct. Now, what about T of 1, comma 2? How will you compute T of 1, comma 2?
Ma'am, transformation T is 8 times x. So x is here 1, comma 2. So
Yes.
we can compute.
So, if you compute this, what will you get? 5 minus 2 and then 2 plus 6. So, you get 3, 8. So, option B is also correct. So, can you all do the C part just like I have done B part? So, it is very similar to B only, right? So, just do this calculation and check what is the answer. For T of 1 comma minus 1, check the answer and tell me. What's the answer?
4, 4, 4 minus.
Are you sure?
Ma'am, 6, comma minus 1.
6 comma minus 1. Correct. Okay. So 5 and then minus into minus is plus. So 5 plus 1, 6. And then 2 minus 3 minus 1. So anyway, this option is incorrect. The transformation T is unique. Of course, the transformation is unique, right? Given the matrix, the transformation is unique. But what do they mean by unique? I don't know here. I guess it is unique only. Because given this matrix here, you will have a unique transformation corresponding to this matrix, right? Okay. Okay, so here few examples are there. So suppose you are having the scaling transformation. Okay, so what's happening to the canonical basis? 1, 0 is mapped to alpha 0. According to this transformation, T of 1, 0 is alpha times of this 1, 0.
0.
So it is simply alpha 0. Okay. Same way T of 0, 1 will be 0 comma alpha. Okay. So The matrix is going to be alpha 0 and 0 alpha. Now, if you have different alphas here, then the matrix is going to be here alpha 1, here alpha 2, because you have T of 1 0 is alpha 1 0 and T of 0 1 is alpha 2 0. That's all. Sorry, 0 alpha 2. Right? So here 0 alpha 2. And for the rotation matrix, see, this rotation matrix is what I wanted to explain earlier. So you are at the point 1 comma 0. You are rotating it to a point here to an angle theta naught. So 1 comma 0 is rotated to an angle theta naught, and you get this point. Now what are the coordinates of this point? So now we have to shift to basic trigonometry. Now you are just rotating. So will the magnitude change? Will the magnitude
No.
change?
No.
No.
What is the magnitude of this part? Can you tell? So this is your origin. So what is this part here? Can you tell me?
1.
1, right? So this side is 1, right? Now here you are having theta naught. I don't know whether this looks like 1. Okay. So this is 1 and this is theta naught. And for this theta naught, this is opposite or adjacent? This part is opposite or adjacent. So let us call,
Adjacent. Yeah.
okay, let us call this point to be maybe x comma y. So this length is your x, right? This is your x, right? We want to see. So the x part is your adjacent side, right? So the x part is your adjacent side. And your y part is opposite to theta, right? Now, what about your cos theta naught? What is the formula for cos theta? Adjacent by
Hypotenuse.
hypotenuse. What is the value of your hypotenuse?
1.
1, right? So you have x by 1, which is nothing but x. Now, what about sine theta? Sine theta, theta naught is nothing but opposite by hypotenuse. So you will have y by 1, so which is here just y. So your x is cos theta naught and y is sine theta naught. So you understand how x comma y, this point is cos theta naught and sine theta naught? Yeah. The same way you can explore that this point is minus sine theta naught cos theta naught. Okay, just use the similar concept here. Draw the triangle, do this cos theta sine theta thing, you will get this. Okay, this part I am leaving it you to work out. Basic trigonometry only, right? So now you see that your t of 0 1, sorry 1 0 is this cos theta naught sine theta naught, and t of 0 1 is minus sine theta naught cos theta naught. Okay, so that is why you have got this matrix. Now once you have the matrix, you know how to find the expression for any t, right? So for t, you know how to find the expression. So those who remember, in the very beginning we saw this example, but we did not do the additivity checking very properly. So those who want to try, maybe you can use this matrix here and try it out. Okay, but anyway, it is something very obvious, but if you want to try it out, here is the matrix from which you can obtain the t and you can verify the additivity. Okay, fine.
So is
So
this linear or not? Rotation.
of course it is a linear transformation, because it only linear transformation we
Really?
are studying here. All the things except the translation, we just stopped all the transformations at that point itself. After that, whatever we are studying, all the properties is only for linear transformation. Okay, once we introduce linear transformation, from that point onwards we are studying only about linear transformations. Okay, so here there are few problems, but we are running out of time. So what shall we do? If you want me to continue, I will continue, otherwise I'll just stop. Shall I stop, and so that we can continue this in the next session?
Please at least slowly scroll down these questions so that we can
These are
See,
nothing but your activity questions. This is there in.
oh,
Yeah, ma'am, I have done these things.
Yeah. So these are your activity questions only. Please go through the activity questions. All these are activity questions. Very simple. Whatever doubts you have, maybe you can ask in the next session. So try to do. I will just post the PDF along with this problem. Try to do it yourself. If you have any difficulty in solving these problems, you can ask it in the next session. Is that fine? Yeah.
Okay, okay.
Fine then. So I will leave these problems for you. If you have doubts, you can discuss it in the next session. So apart from these problems, are there any other doubts from this session?
yeah, not from this session, but the week one, yeah, I can ask later. I don't want to take too much of time now.
Okay.
But please see whether it could, because whatever you were taught, they are pertaining to week two, correct?
Yeah, yeah. So just
So
will
if they can postpone the, I mean, our deadline, that would be helpful, at
I'll
least for
just check.
me. I don't know about the other
Okay,
peers.
I'll check that. Okay,
Thank you very much.
fine. So if no one is having any doubts in this session, shall we wind it up? Okay. Yes, someone is raising your hand by mistake, or you want to ask something? Okay, maybe by mistake. All right, then. See you in the next session.
Thank you, ma'am.
Thank you.
Thank you,